Think for a moment about the incredible shrinking act that's been happening with our electronics. Your smartphone, for instance, packs more processing power than computers from decades ago, all thanks to, well, the ever-increasing complexity and miniaturization of semiconductor chips.
Mm.
It really makes you wonder, doesn't it? How on earth do they build these things? How do you precisely assemble billions of components that are almost unimaginably tiny?
That's precisely the fascinating challenge we're going to unpack today. You're spot on.
Yeah.
The level of intricate detail is astounding.
Yeah.
And as all of us expect more from our devices, faster speeds, greater memory, longer battery life, the underlying manufacturing techniques for these chips have to, well, keep pace.
Which brings us to some truly groundbreaking work coming out of the University of Massachusetts Amherst. They've pioneered a completely new method for aligning 3D semiconductor chips with a level of precision that's, frankly, kind of hard to believe.
Absolutely. And for you listening, to really grasp why this is such a significant leap, let's quickly revisit what these semiconductor chips actually do.
Good idea.
They are the fundamental building blocks of our digital world, right?
Right.
Responsible for processing information, storing data, transmitting signals in virtually all the electronic devices you use.
Everything.
Pretty much. And for a long time, the industry has relied on building these complex circuits on a single layer, what we call 2D chip designs.
But as we're demanding more and more from our devices, it feels like those flat designs are bumping up against some hard limits, right?
Yeah.
It's like trying to fit an entire city onto a single map. Eventually, you need to build upwards.
Exactly. To achieve greater power and more features in smaller and more efficient devices, the future is in 3D integration.
Stacking them up.
Stacking them up. It involves stacking multiple of those 2D chips on top of each other. By doing this, the connections between different parts of the circuit become much shorter,
Okay.
which leads to faster performance and lower energy use. Think of it like building that city vertically. And this is where the seemingly arcane problem of alignment becomes absolutely critical.
Okay, so we're talking about carefully stacking these incredibly thin chips. Just how accurately do they need to line up? This isn't like stacking pancakes, is it?
No, far from it. We're talking about needing alignment down to the scale of tens of nanometers.
Tens of nanometers.
Yeah. Now, for a bit of perspective, a nanometer is 1/1000th of a meter.
Oh.
We're dealing with dimensions that are approaching the size of individual atoms.
Okay.
And this alignment isn't just about lining them up side by side, X and Y. It also includes the precise vertical distance, the z-axis, between each layer.
That sounds like an almost impossible task. So what were the traditional ways of doing this, and what were the stumbling blocks?
Right, so the conventional approach, as the researchers themselves point out, has been to use high-powered microscopes.
Makes sense.
They use them to locate specific alignment marks on each chip layer, usually something like crosshairs or precisely defined corners. The goal is to get these marks to overlap as perfectly as possible.
That sounds logical, like carefully lining up markings on two pieces of paper. But I can already imagine there might be some inherent difficulties.
You're thinking along the right lines. As Amir Arababi, one of the senior researchers, explains, a key challenge is that a standard microscope can't simultaneously bring into sharp focus alignment marks that are on different layers.
Because they're at different depths.
Exactly. The vertical distance between these layers can be hundreds of microns. That's thousands of times larger than the nanoscale precision that's required.
Right.
So the microscope has to constantly refocus as you look at different layers. And every time that happens, there's a risk of the chip subtly shifting and becoming even more misaligned.
So it's like trying to perform delicate surgery while constantly adjusting your focus. That sounds prone to error.
Precisely. And Mariam Garamani, the lead author, also points out another fundamental hurdle, something called the diffraction limit of microscopes.
The physics limit.
Yeah, a basic physical property of light that essentially limits the smallest details you can clearly see.
Yeah.
For standard optical microscopes, that limit is around 200 nanometers.
Okay.
So when you need alignment that's significantly finer than that, down to those crucial tens of nanometers, traditional microscopes simply run into a physical wall. It's like trying to see something smaller than the wavelength of light itself.
So these incredibly tiny misalignments, things we couldn't even dream of seeing with our own eyes, can have a really significant negative impact on how these advanced electronics actually perform.
Absolutely. Even minuscule errors in alignment can lead to decreased performance, increased energy consumption, and in some cases, even a complete failure of the entire chip.
Ouch.
Which is why achieving this ultra-precise alignment in 3D chip manufacturing has been such a major bottleneck for the industry.
Okay, that gives us a really clear picture of the problem. So now let's dive into this new method from UMass Amherst. They're using lasers and holograms. Sounds like something straight out of science fiction.
It does sound advanced, doesn't it? And it is a fundamentally different approach. What's particularly innovative is that their method doesn't rely on any physical movement of parts during the critical alignment phase.
No moving parts. How?
Instead, they engineer these incredibly tiny, precisely shaped structures called concentric metal lenses directly onto the surfaces of the semiconductor chips.
Metal lenses.
I think of them as microscopic lenses made of metal, but with very specific optical properties. Their unique design is really key here.
So these tiny metal things act as the alignment markers instead of crosshairs.
Kind of, yes.
Yeah.
When a laser beam is shown through these patterned metal lenses on the stack of chips, it creates what are called interfering holograms.
Interfering holograms, right.
Now, a hologram is more than just a static image. Think of it as a complex pattern of light waves interacting, carrying a ton of information.
Okay.
And what's truly remarkable here is that the way these holograms interfere reveals a very precise picture of how the chips are aligned relative to each other.
So just by analyzing the light pattern that comes through, you can tell if they're lined up.
Exactly. As Mariam Garamani explains it, this interference image shows if the chips are aligned or not, as well as the direction and the amount of their misalignment.
Wow.
It's like having an extremely sensitive visual indicator. It tells you exactly how well the layers are stacked, even if the error is way too small for a microscope to clearly see.
And the level of precision they've achieved is just staggering. The research mentions 0.017 nanometers for side-to-side alignment.
And 0.134 nanometers for the vertical gap.
Those numbers are almost impossible to comprehend. 0.017 nanometers.
They are truly remarkable. The researchers initially set a goal of achieving around 100 nanometer precision.
Which would have been good already.
Which itself would have been a significant step forward, yeah. But they far surpassed even their own ambitious expectations.
Clearly.
As Amir Ababi so eloquently put it, consider you have two objects. By looking at the light that goes through them, we can see if one moved by the size of an atom with respect to the other one.
The size of an atom.
Yeah. That really gives you a sense of the extraordinary sensitivity of this technique.
That's just mind-boggling. So our eyes couldn't even come close to detecting errors that small, could they?
Not even remotely. The article mentions that the human eye can typically resolve details down to maybe a few micrometers.
Which is thousands of nanometers.
Exactly. But even misalignments much smaller than that, like a lateral shift of just 10 nanometers, create distinct holographic patterns that computers can readily analyze.
So the computer sees the misalignment in the hologram pattern.
Right. The system can detect and quantify misalignments that are far, far beyond the limits of human vision or standard microscopes.
Okay, so this new method offers a monumental increase in accuracy for 3D chips. But what are the tangible benefits for, someone like me just using everyday electronics? Why should we care?
Well, there are several really compelling reasons. Firstly, and perhaps surprisingly, this tech has the potential to substantially reduce the cost of manufacturing even traditional 2D chips.
Oh, really? How so?
The improved alignment accuracy during fabrication can lead to higher yields, fewer defective chips coming off the line.
Ah, less waste.
Exactly, which ultimately lowers production costs. So these kinds of advancements behind the scenes can, eventually lead to more affordable electronics for everyone.
That's a really interesting point. We often think about these cutting-edge things only impacting the, super high-end gadgets, but better manufacturing helps everywhere.
Right. And more directly related to the future, this level of precise alignment is absolutely crucial for enabling the widespread development and manufacturing of those next-gen 3D photonic and electronic chips we talked about.
The stacked ones.
The stacked ones. Without this kind of accuracy, building complex, reliable 3D integrated circuits just wouldn't be practical. This technology is like a key that unlocks the door to more powerful, more energy-efficient devices in the years to come.
Like faster phones with longer battery life.
That's the kind of thing, yeah. Think about how often you hear about wanting that this is the sort of fundamental advancement that makes those improvements possible down the line.
So this isn't just about making today's chips slightly better. It's really about paving the way for a whole new era of electronic technology.
Precisely. And Amir Arbabi also emphasizes the significance for the companies that actually make the semiconductor fabrication
Think
tools.
tool makers.
Yeah. By offering a more precise and potentially more cost-effective alignment solution, it could lower the barriers to entry for smaller, more innovative startup companies.
Ah, helping the little guys compete.
Could be. It potentially democratizes access to this foundational technology a bit more. It's not just the giant corporations that stand to gain.
That's a fascinating angle.
Absolutely. But what I found particularly intriguing is that the potential applications of this laser and hologram method extend far beyond just chip manufacturing.
Oh, really? Like what?
Well, the researchers realized that this incredibly sensitive alignment technique could be adapted to create extremely precise displacement sensors.
Displacement. Measuring tiny movements.
Exactly. As Amir Arbabi explains, many physical quantities that you want to detect can be translated to displacements, and the only thing you need is a simple laser and a camera.
Huh. So instead of using it to line up chips, you use it to measure how much something else moves.
Precisely. Take a pressure sensor, for instance. You could have a very small, thin membrane that flexes just slightly
Tiny flex.
in response to pressure changes. By using this laser and hologram system to measure that minuscule movement, you could create a highly sensitive and accurate pressure sensor, and maybe much more affordably than current tech.
That's a clever leap. So any physical change that results in a tiny shift or movement could potentially be measured this way. Vibration, heat.
Exactly. The researchers suggest it could be applied to tracking all sorts of things. Subtle vibrations in machinery, minute expansions or contractions due to heat changes, even very small accelerations. This opens up the possibility of creating a wide array of affordable, compact sensor technologies for diverse fields. Industrial monitoring, environmental sensing, maybe even advanced medical diagnostics someday.
Wow, so this fundamental breakthrough in how we build computer chips could also lead to a whole new landscape of sensing capabilities. It's amazing how seemingly niche research can have such broad, maybe unexpected implications.
It truly is. This work out of UMass Amherst provides a powerful new tool. It not only tackles a critical challenge in advanced electronics, but also unlocks exciting new possibilities in completely different domains.
Okay, let's bring it all together then. The key takeaway here is this novel method, right? Using lasers and holograms for incredibly precise alignment of 3D semiconductor chips. It overcomes the fundamental limits of the old microscope methods.
Right.
And the potential benefits are huge, driving down manufacturing costs, even for 2D chips, paving the way for next-gen 3D electronics, and maybe even spawning a whole new era of affordable, super-sensitive sensors.
That's a perfect summary. What's so compelling is seeing how a solution to a very specific technical problem,
A really specific one.
yeah, in a highly specialized field, can have such far-reaching potential. It impacts the technology we all rely on and could inspire entirely new innovations we haven't even fully imagined yet.
It really makes you think about the future, doesn't it? I mean, if we can achieve this level of control and measurement, near atomic level, basically, what other fields could be revolutionized? Could we see similar breakthroughs in medicine or materials science, or even our fundamental understanding of the physical world? It's truly exciting to consider the possibilities that such extreme precision could unlock.
That's a very thought-provoking question to end on. The ability to manipulate and measure at such a fine scale genuinely opens up a realm of possibilities we're only just starting to explore.
Yeah.
It really underscores the critical importance of fundamental scientific research, doesn't it? How breakthroughs in one seemingly narrow area can have unforeseen and transformative consequences in countless others.
Absolutely. Well, this fascinating research was published in the journal Nature Communications back on October 14th, 2024, and it had funding support from the U.S. National Science Foundation.
Important to acknowledge.
Definitely. And if you're interested in digging into the really technical details, you can find the full paper using the DOI, the Digital Object Identifier. We'll put that in the notes, but it's 10.1038 01467 024 532 19 is definitely worth a deeper look if you want the real nitty-gritty.